Germany, 1939. In a secret bunker on the German-Polish border, Nazi agents were overseeing the production of a recently discovered chemical they'd codenamed Substance N. It boiled when exposed to air, exploded in contact with water, was lethal when inhaled, and decomposed to release deadly hydrofluoric acid. When loaded into a flamethrower and ignited, it could burn at temperatures over 2,400 degrees Celsius. The plan was to arm troops with Substance N and use it to melt Allied bunkers into hot porridge. However, even the German soldiers eventually realized the extreme dangers of the chemical. Experiments with Substance N were discontinued because the Nazis deemed it too dangerous to work with. This should give you a sense of the level of danger we're dealing with when discussing the most hazardous chemicals in the world. These substances can explode upon contact, are so poisonous that even a minuscule amount inhaled can be fatal, and disable you due to their overwhelmingly repulsive smell. Even the Nazis, known for their extreme methods, considered these chemicals too insane to handle. Let's begin with what the Germans had in that secret weapons bunker. They initially aimed to produce 90 tons of the substance every month but only managed to make about 30 tons throughout the war. They had concocted chlorine trifluoride, the most aggressive fluorinating agent known to humanity. Fluorinating agents break apart other molecules to replace their hydrogen atoms with fluorine, resulting in what chemists call a violently exothermic reaction. In this case, it was known as a fluorine fire. Chlorine trifluoride is even more dangerous than fluorine gas, which is already considered highly hazardous. It also serves as a better oxidizer than oxygen itself. Oxidizers are compounds that snatch electrons from other chemicals in a reaction, making combustion possible. Chlorine trifluoride is so proficient in this role that it can burn materials deemed non-flammable by sane individuals, such as bricks or asbestos. It can burn even previously burned substances. Oxidizers are also used to ignite rocket fuel. However, when U.S. scientists briefly considered chlorine trifluoride as a fuel in the early 1950s, they quickly realized it was a terrible idea. During the first attempt to ship chlorine trifluoride in bulk, the steel tank cracked, causing a ton of the chemical to spill. It burned so intensely that it ate through an entire concrete floor and a meter of soil and gravel beneath it. Semiconductor companies still manufacture chlorine trifluoride, using it to clean their equipment meticulously. The good news is that you can safely store chlorine trifluoride in a regular, airtight steel drum. However, extreme caution must be exercised because it immediately scorches the interior lining of the container, leaving behind a non-reactive plating of metallic fluoride. Non-reactive is not a word we'll need when discussing the next chemical on our list, azetoazide, the most explosive chemical compound ever created. This highly reactive compound is part of a class of chemicals known as high nitrogen energetic materials. Azetoazide's explosive nature stems from nitrogen's innate desire to remain undisturbed. Nitrogen atoms bonded to each other form one of the most stable molecules on Earth, featuring a powerful triple bond that nature usually breaks only through phenomena like lightning strikes. This bond strength means that when two nitrogen atoms come together, they release immense energy. For simplicity, you can see its explosive potential in a molecule of azetoazide, or AA. With 14 nitrogen atoms, none of them in a triple bond due to the molecule's structure, they are in a loosely bound, high-energy state, yearning to transition to a more stable, lower-energy state. This transition releases substantial pent-up energy, making AA highly reactive and explosively dangerous. It is so sensitive that its level of sensitivity cannot even be measured. German chemists, assisted by the U.S. Army, synthesized it in 2010 to develop more energetic compounds. Their initial report stated, "The sensitivity of C2N14 is beyond our capabilities of measurement. Even the smallest possible loadings in shock and friction tests led to explosive decomposition." Simply put, azetoazide explodes when moved, touched, dispersed in a solution, left undisturbed on a glass plate, exposed to bright light or X-rays, set in a spectrometer, or even without apparent cause. It is an incredibly volatile compound. Even when kept in a shockproof, explosive case in a dark, climate-controlled room, it can still spontaneously detonate. The lead scientist who synthesized it described it as a fascinating discovery, but for anyone working with acetoazide, waking up each morning with all their fingers intact would be an exciting discovery. Next on the list is dimethyl cadmium, an organometallic compound where carbon is bonded with the metal cadmium. Gram for gram is likely the most toxic chemical in the world, possessing acute and chronic effects that can kill you both immediately and in the long run. It was first synthesized in 1917 by Erich Krauss, a German pioneer in metal organic chemistry who tragically died at 37 in his lab after accidentally inhaling chlorine. Before his demise, he managed to report his discovery of dimethyl cadmium. When inhaled, dimethyl cadmium is instantly absorbed into the bloodstream, acting as a chemical carrier for toxic cadmium compounds to travel throughout the body. Due to its efficiency in exploiting the bloodstream, it quickly affects highly vascularized organs such as the lungs, kidneys, and liver. It forms compounds that strip electrons from cells' atoms, causing severe damage. Suppose one survives the first few hours after exposure, there's no reason to feel optimistic. Dimethyl cadmium is also highly carcinogenic, leading to cancer as a spiteful aftermath. As an airborne vapor, just a few millionths of a gram per cubic meter of air surpasses legal safety limits. If spilled, cleaning it becomes a dangerous challenge. Water reacts with dimethyl cadmium, generating intense heat and flammable hydrogen gas, resulting in an explosion. Attempting to sweep it up can cause ignition due to friction. Waiting for it to decompose leads to the formation of dimethyl cadmium peroxide, a friction-sensitive explosive. You would be just one shoe scuff away from a catastrophic explosion. Moreover, the chemical emits a foul, unpleasant, metallic, and disagreeable odor. Now, let's discuss thioacetone, which may not explode, start fires, or cause cancer, but it earns its place on the list as the world's smelliest chemical. Thioacetone is a thiol, an organic compound where a carbon atom is bonded to a sulfur-hydrogen pair. Thiols are notorious for their repulsive odors. A skunk spray, for instance, utilizes two different thiols to achieve its eye-watering effect. Most sulfur-containing compounds are associated with the smell of decaying meat, which explains our sensitivity to their detection. Thioacetone, however, takes the prize for having the most unbelievably foul smell. Just a single drop of this substance can almost instantly be smelled from half a kilometer away. In the 196 zeros, a vial of thioacetone fell off a shelf in a research lab, causing people in buildings 200 meters away to experience nausea and vomiting. The most extreme case occurred in the German city of Freiburg in 1889, where chemists at a soap factory were working on a larger molecule called trithioacetone, used as a flavoring and fragrance. When they inadvertently broke it apart into thioacetone, workers started falling ill, and spontaneous outbreaks of vomiting were reported in the surrounding neighborhoods. The situation escalated to the point of evacuating the entire city. Due to its overwhelmingly repugnant odor, scientists are not eager to delve further into the study of thioacetone and other thiols. Lastly, we have fluoroantimonic acid, the most corrosive and dangerous acid ever created by humanity. Fluoroantimonic acid is classified as a superacid. Acidity refers to an acid's ability to donate a proton to nearby molecules. A proton is a hydrogen atom that has lost its electron. The strength of an acid depends on its willingness to donate this proton. Weak acids, like acetic acid, vinegar, hesitate to protonate other molecules and do so slowly. In contrast, strong acids like sulfuric acid readily donate protons. Fluoroantimonic acid, however, surpasses all other acids in terms of strength. It is 10 quadrillion times stronger than sulfuric acid. Once it loses its hydrogen atoms, the remaining fluorine and antimony atoms in the molecule tear through surrounding molecules, stripping electrons and leaving behind a path of destruction. It has a particular affinity for bonding with calcium, meaning that after it penetrates the skin and muscles, it can eat through bones. Due to its extreme reactivity, conducting experiments with fluoroantimonic acid is incredibly challenging. It corrodes glass, destroys fume hoods, and poses a significant hazard to researchers. It can only be stored in Teflon containers, as Teflon's carbon-fluorine bonds are the strongest in organic chemistry. Scientists are limited to observing fluoroantimonic acid from a safe distance, acknowledging its immense danger. In conclusion, the chemicals discussed here exemplify some of the most hazardous substances known to humanity. They possess properties that make them explosive, toxic, corrosive, and incredibly odorous. Their dangerous nature has been recognized even by the Nazis, who decided to discontinue experiments with chlorine trifluoride due to its extreme dangers. These chemicals serve as reminders of the perils associated with working with highly reactive and unstable compounds. That's it for today. We hope you liked our video. And for more informative videos like this, please subscribe to our channel. Thank you.